So now we've talked about the distribution of the beta 1 hat, we might want to think about how we can get more efficient or lower variance estimates. And to do that, let's think about what the variance looks like. The variance of beta 1 hat is equal to the variance of u divided by the sum of the x minus x bar squared. And the sum of the x minus x bar squared may look familiar because we've seen something similar when we looked at the s squared, the unbiased estimator of the population variance. The s squared is 1 over n minus 1 times by the sum of the x minus x bar squared. So we could write this variance of beta 1 hat in terms of s squared and the number of observations. So we could replace the sum of the x minus x bar squared with n minus 1 times by s squared. Now, intuitively what this tells us is that one way of trying to make the estimates more efficient is to increase the sample size. If we increase the sample size, the variance will get smaller. But also, s squared is an unbiased estimator of the population variance of x. So another way of trying to make the estimates more efficient is to increase the variation in the explanatory variable, increase the variability of the x's. Now, increasing the sample size intuitively makes a lot of sense. I've run a simulation in order to illustrate the impact of different sample sizes on the variability of the OLS estimates. The orange distribution represents the distribution of estimates when we had 25 observations, the blue when we've got 100 observations, and the green when we've got 500 observations. And you can see that as the sample size gets larger, the distribution gets squeezed, the variance gets smaller. However, what about the variation in the x variable? Now, in order to see intuitively what's going on, let's have a look at two, again, small simulations where we've just taken one set of observations, one with a very small variability in the x, one with a very large variability in the x. So in these two cases, the data is generated using the same data generating process. In the top example, the variability of the x's is very, very small. In the bottom example, the variability of the x's is much, much larger. Now, what you can see in the bottom example is that there's much more signal of the overlying, or there's a much better signal of the underlying relationship between x and y. Because we've got more variability in the x, you can see a much stronger trend in the data. Even though the top data is generated using the same data generating process, there's much less signal. There's much more noise and much less signal in the data. So in this case, we're going to get much less precise estimates. We're going to get much more variability across samples simply because we're not getting as good a signal of the relationship between the two variables. We can illustrate this again using simulations. When we have a relatively small variance, when the variance of the x was 0.1, there's a very wide spread of estimates that you get of your beta 1 hat. On average, it's still 3. The true beta 1 is 3. The average of our estimates is 3. But there's a lot of variability across samples. When we increase the variance with the blue curve, that's giving us less variability in our beta 1 hats. When we increase the variance again to the variance being 10 with the green curve, we're decreasing the variance again. As the variability in that x increases, the variability in our estimates goes down.